Hello, everyone. I'm going to give a quick introduction to magnetism. So this goes along with lecture 19 notes. And on the first slide here, you can see a picture of a magnet. It's got a north pole and a south pole. So let's talk about magnets. Magnets are things that you've probably experienced. And one of the defining features of a magnet is that it has two poles, the north pole and the south pole. And the North Pole and the South Pole act a lot like positive and negative charges, but not exactly. So if I put a North Pole next to a North Pole, those two magnets will repel, just like two positive charges or two negative charges. And if I put a North Pole next to a South Pole, those two magnets will attract. So what's the difference? Why can't we just say that these are the same thing as positive and negative charges, or that they act just like positive and negative charges? The difference is that you always have north and south together. You can never have a magnet that just has one or the other. So if I have something that has some positive and negative charge, and I cut it in half, I'm left with a positive charge and a negative charge. If I take a bar magnet with a north and south pole, and I cut that bar magnet in half, I'm left with two little bar magnets that each have their own north and south pole. So it's not possible to isolate just a north pole or just a south pole of a magnet. They always come together. So what are magnets? Well, right now, just know that magnets exist. Sometimes they occur naturally. We can make them, and we're going to learn a lot more about how they work shortly. The other feature of magnets is that they create a magnetic field. Just like charges create an electric field, magnets create a magnetic field, and the field lines for magnets point north to south. And so you're going to find field lines that look like this. They go from the North Pole to the South Pole. And an important fact about magnetic field lines is that they never start or stop. So unlike the electric field, which can begin on positive charges and end on negative charges, the magnetic field lines have to form closed loops. And so inside the magnet, they're actually circulating back around, forming closed loops. They never start and they never stop. Sort of like that. So we'll see more examples a little bit later. Okay, so it turns out that magnets are complicated. Magnets, as we know them with north and south poles, were discovered hundreds and hundreds of years ago, used for navigation and compasses, et cetera, et cetera. The Earth has a magnetic field that was known for a long time. But how it works and what's its connection to electricity was not discovered until relatively recently. And so we're actually going to start there. We're going to start and go backwards in time. We're going to say, here's the simplest thing we know about how magnetism affects electric charges. And the difference between electricity and magnetism here is that magnetism affects moving charges, not stationary charges. So moving charges will create a magnetic field, and a magnetic field will exert a force on moving charges. But it won't exert a force on a stationary charge, and a stationary charge won't create a magnetic field. It will create an electric field. The magnetic field is called B, capital B. It's a vector, just like the electric field. So now let's talk about what sort of force is exerted on these moving charges. So again, this is something different than your everyday experience with magnets pushing on each other. We're talking here about magnetic fields pushing on moving charges. We don't actually experience that much in our day-to-day life. So to talk about this, we need to introduce what's called the Lorentz force and the right-hand rule. And all of this is taking place in 3 dimensions. And so we need a couple new symbols. So we're used to drawing vectors as arrows. So here's one vector, and there's a vector perpendicular to that vector. It's at a right angle. But there's another vector perpendicular to those 2 vectors. In fact, there's 2 vectors perpendicular. There's the vector coming out of the page, which we're going to denote by a circled dot. And there's the vector going into the page, which we're going to denote by a circled X. And these are supposed to remind you in a mnemonic way of arrows. The left-hand one, so the outward direction is supposed to be the tip of an arrow coming right at you. And the inward pointing one is supposed to be you looking at the tail feathers on that arrow. So it's not very graphically accurate, but it's supposed to help you remember which one is which. So with that, how do we talk about the magnetic force? So the magnetic force is also called the Lorentz force. I'll call it F mag for magnetic. And we write it in the following way: charge, velocity, cross, magnetic field. And this thing here is new. It's called the cross product. And it's a way of taking 2 vectors and making a 3rd vector out of them. It's like multiplication, but it's a little bit different. The order matters, and the direction is not what you'd expect. One thing is, how do you find the magnitude? So don't get magnitude confused with magnetic. Here, this is the magnitude of the magnetic force. I multiply all the magnitudes, so I have charge times the magnitude of velocity, which is speed, times the magnitude of the magnetic field, which is just capital B. And the cross product is telling me that I need to include a sine theta, where that's the angle between those 2 vectors. So if I go over to my picture here, maybe this is the velocity vector, this is the magnetic field vector, then theta here would be 90 degrees and sine theta would be 1. If I have a smaller angle, then I'll have a smaller sine theta. And the more parallel V and B are, the smaller the force, which is kind of interesting. Then we have to decide the direction. The direction of the magnetic force is perpendicular to both V and B. And so given our diagram up here where we have the velocity vector and the magnetic field vector, there are 2 choices. You could have the force pointing out of the page, or it could point into the page. And how do you decide? You have to use the right-hand rule. So I'm going to try and describe it in words. There's some diagrams in the book for a slightly different approach. You can pick which one you like best. The right-hand rule, first you take your right hand. It's very important to start with your right hand. Point your fingers along the velocity and then curl them towards the magnetic field. And so when I do that, I start with my fingers pointing up and to the right, and I curl them towards my palm, down and to the right. That means I have to twist my wrist around until my thumb is pointed in to the page. So fingers along V, curl them towards B, thumb is pointing in to the page with my right hand. If I tried it with my left hand, I'd get the opposite answer. The right hand rule is telling you, use the answer you get from your right hand. That's how you pick. That's telling me the result of V cross B. Then I have to decide, well, is that the direction of F? It depends on if Q is positive or negative. So if Q is positive, then that's the right answer. If Q is negative, then I have to flip the answer that I get from the right-hand rule. Again, that's because the right-hand rule tells me what's the direction of V cross B, but I really need the direction of Q times V cross B. So if I multiply that by a negative number, I flip the direction around. Okay. All right. One last thing. We're going to talk about making magnetic fields. And to make a magnetic field, again, you need moving charges. Not stationary charges won't do, you need moving charges. And moving charges are also called currents. And so I'm going to talk first about the magnetic field created by a long straight current. So I have a current flowing along a long straight wire. And so I'm going to draw it from two directions. Everything is 3D now when we're talking about magnetism. And the end-on view is the current. I'll draw it like that because it's coming right out at you. So there's another right-hand rule that you use for making the magnetic field. And this is what you do. You take your thumb and put it along the direction of the current. Again, it's your right thumb, not your left thumb. And you curl your fingers around that direction. The direction that your fingers curl is the direction that the magnetic field lines are going. And so that's easiest to see on the end view. Over here, I have my thumb, my right thumb sticking out, and my fingers are curling counterclockwise around. And that means my magnetic field lines are circulating that way. Now, if I'm looking at it from the side, above the wire, the magnetic field is coming out at me. And below the wire, it's going back into the page. That's in the plane of the current. And if I'm hovering sort of somewhere over the paper, the magnetic field would be pointing down. And if I'm hovering inside behind the chalkboard, the magnetic field would be pointing up. The magnetic field lines are sort of twisted relative to electric field lines. They tend to go around things rather than in and out of things. All right, that's my introduction to magnetism. I will post another video about lecture 20 on how this applies to magnets themselves and about how we think about the forces on loops of current, because that's very important both for understanding magnets and also for practical applications of magnetism. Thanks.